My name is Holden Mays, and this is my video lab report for Lab 2 for Physics 2212 at Georgia Tech. This report will cover the lab in 6 sections, beginning with an introduction to the lab, followed by assumptions made during the lab, the experimental data used in the lab, an explanation of the computational model and the calculations used in it, and ending with a couple of discussion questions. The goal of this lab was to more accurately approximate the magnitude of the charge of the piece of floating tape used in Lab 1. During Lab 1, 2 pieces of tape were given negative charges approximately equal in magnitude, and Coulomb's law was used to approximate that charge by setting the electromagnetic force acting on one piece of tape equal to the force due to gravity acting on it, treating each piece as point charges. By instead treating each piece of tape as a line of multiple uniform point charges, a more accurate approximation of the net charge of a single piece of tape can be acquired by comparing the force due to gravity acting on one piece of tape to a newly calculated electromagnetic force. Similarly to the first lab, Coulomb's law and Newton's second law of physics are the main laws looked at in this lab. A more accurate net charge can be found by calculating a new net electric force using the net charge acquired in Lab 1, comparing that net electric force to the force due to gravity, and then adjusting the net charge used in calculations until the resulting net electric force is equal in magnitude to the force due to gravity. Several assumptions need to be made in order to successfully use Coulomb's law in this lab. Firstly, the force due to gravity and the net electric force will be the only forces acting on a piece of tape. Secondly, each piece of tape will be treated as a uniform line of point charges, each with equal magnitude of charge and an equal distance from each other. Third, both pieces of tape are equal in total charge and consist of the same number of point charges. The measurements used in this lab listed here are taken directly from the first lab. The computational models here depict the results of this lab when the net charge acquired during Lab 1 is used in the calculations versus when the new net charge acquired experimentally during this lab is used. In the models, the line of red point charges represent tape B, the floating piece of tape, while the line of blue point charges represents tape A, the charged piece of tape and tape B's surroundings. Each line consists of 10 point charges. The green arrows represent the electric field located at each individual point on tape B as a result of all 10 of tape A's points, calculated through superpositioning by summing the vectors that represent the electric fields caused by tape A. The white arrow represents the net electric force acting on tape B, sized proportionally to the yellow arrow, which represents the force due to gravity acting on tape B. The glowscript code depicted here calculates the electric field caused by all of tape A's points at each individual point on tape B using Coulomb's law, summing together the 10 individual electric fields at one point and assigning a green arrow that points in the same direction as the net electric field. Once that is done 10 times, one for each point on tape B, those electric fields are again summed together and used to calculate the net electric force acting on tape B. That net electric force is then assigned an arrow and printed alongside the force due to gravity, allowing a comparison to be made between the two. A piece of tape floating in equilibrium should have the two forces be equal in magnitude. Using the net charge of tape B found during Lab 1 produced a net electric force significantly smaller than the force due to gravity acting on tape B, indicating that the net charge used needed to be greater in magnitude. Making progressively smaller adjustments to the net charge used until the net electric force was equal to the force due to gravity, tape B was found to have a net charge of approximately 8.69785 times 10 to the negative 9 coulombs in magnitude. Using a single point model resulted in a significantly lower net charge than a line charge model. The line charge model requires a larger net charge to produce an electric force equal to the point charge model because, when spread out, the distance between any 2 points is typically slightly greater than merely the distance between the 2 pieces of tape, since some distance in the x direction must be taken into account. This additionally produces some electric force in the x direction that gets cancelled out. The line charge model is likely more accurate since the piece of tape is a line of approximately uniform charge.